While it is not typically recommended to install ground rods at parking lot lights, there are circumstances where it may be necessary or beneficial. If ground rods are installed, connect the equipment grounding conductor from the conduit to the ground conductor from the ground rod. Do not connect the ground conductor from the ground rod directly to the light fixtures. If ground rods are not installed, bring an insulated equipment grounding conductor from the panel board to the light fixtures. Connect the equipment grounding conductor to the grounding bus of the light fixture. The equipment grounding conductor should be sized per Article 250 of the National Electrical Code. Connecting the equipment grounding conductor from the conduit to the ground rod ensures that the conduit and all electrical components within it are properly grounded. Isolating the ground conductor from the ground rod from the light fixtures prevents any potential voltage differences from being introduced into the lighting system. By bringing an insulated equipment grounding conductor from the panel board, the grounding integrity of the lighting system is maintained even if the ground rod is not in place or is damaged. The ground rod should be driven into the earth to a depth of at least 8 feet or 2.4 meters in accordance with NEC Article 250.54. The ground rod should be made of copper-clad steel and have a minimum cross-sectional area of 0.5 inch squared or 30 millimeters squared. The ground conductor from the ground rod should be sized per NEC Article 250.66 and connected to the panel board grounding electrode system. Considering these points, firstly, we look at the purpose of grounding. Grounding serves two primary functions: firstly, personnel safety, and secondly, equipment protection. Effective grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly clear the fault, minimizing the risk of electrical shock and equipment damage. Secondly, when installing ground rods, it is crucial to adhere to NEC requirements to ensure the effectiveness of the grounding system. Article 250 of the NEC provides detailed guidelines on grounding and bonding. Thirdly, the size of the grounding electrode conductor, which connects the ground rod to the grounding electrode system, is determined by NEC Table 250.66 based on the size of the ungrounded conductors at the service. Sizing it correctly ensures that it can adequately carry fault current. Fourthly, the depth and material of the ground rod are also specified in the NEC. As previously stated, a ground rod must be at least 8 feet long and made of materials like copper or copper-clad steel to resist corrosion and provide a reliable electrical connection to the earth. Fifthly, when connecting the equipment grounding conductor from the conduit to the ground rod conductor, use appropriate connectors listed for grounding and bonding. Ensure that all connections are tight and corrosion resistant to maintain a low impedance path. Sixthly, when bringing an insulated equipment grounding conductor from the panel board, it should be sized according to NEC Table 250.122, which is based on the rating of the overcurrent protective device in the circuit. The equipment grounding conductor should run with the circuit conductors and be connected to all metallic enclosures and equipment. Seventhly, isolating the ground rod conductor from the light fixtures aims to prevent circulating currents and potential voltage differences from being introduced into the lighting system. This helps reduce the risk of stray voltages that could cause nuisance tripping of ground fault circuit interrupters or pose a shock hazard. Eighthly, it is essential to understand the difference between grounding and bonding. Grounding connects electrical equipment to the earth, while bonding connects metallic parts to create an electrically conductive path. Both grounding and bonding are necessary to ensure electrical safety. Ninthly, regular inspection and maintenance of the grounding system are crucial to ensure its continued effectiveness. Check for signs of corrosion or damage to ground rods, conductors, and connections. Test the ground resistance to ensure it remains within acceptable limits. Tenthly, ground rods are typically supplemental grounding electrodes and are not intended to be the primary grounding electrode for a building or structure. The primary grounding electrode is usually a metal underground water pipe or a concrete-encased electrode. Understanding the specific requirements and recommendations for grounding parking lot lights, it is important to consider several factors such as the soil conditions, local electrical codes, and the specific characteristics of the lighting system. Poor soil conductivity may require the installation of multiple ground rods or the use of ground-enhancing materials to achieve the desired ground resistance. Local electrical codes may have additional requirements or restrictions regarding the installation of ground rods and grounding systems. The design and characteristics of the lighting system, such as the type of fixtures, the voltage level, and the presence of electronic ballasts, may influence the grounding requirements. It is crucial to consult with a qualified electrical engineer or contractor to ensure that the grounding system is properly designed and installed. Proper grounding is essential for the safe and reliable operation of electrical equipment. A well-designed and maintained grounding system can minimize the risk of electrical shock, equipment damage, and fire hazards. Grounding provides a low-impedance path for fault current to return to the source, allowing overcurrent protective devices to quickly clear the fault. In the event of a ground fault, current will flow through the grounding system back to the source, causing the overcurrent protective device to trip and to energize the circuit. This helps to prevent dangerous voltages from appearing on metal enclosures or equipment, reducing the risk of electrical shock. Equipment grounding conductors, often referred to as EGC, play a crucial role in the grounding system. These conductors provide a low impedance path for fault current to flow back to the source in the event of a ground fault. EGC are typically made of copper or aluminum and are sized according to the rating of the overcurrent protective device in the circuit. They are connected to all metal enclosures and equipment, providing a continuous grounding path throughout the electrical system. Ground rods are often used as supplemental grounding electrodes to improve the overall effectiveness of the grounding system. Ground rods are typically driven into the earth near the equipment being grounded and are connected to the grounding system with a grounding electrode conductor. The purpose of a ground rod is to provide a low impedance path to earth, helping to dissipate fault current and reduce the risk of electrical shock. The NEC specifies the requirements for ground rods, including the minimum size, material, and installation depth. It is essential to follow these requirements to ensure that the ground rod is effective in providing a low impedance path to earth. Grounding electrode systems are designed to provide a lower impedance path to earth for fault current. These systems typically consist of one or more grounding electrodes, such as ground rods, metal underground water pipes, or concrete encased electrodes connected together with grounding electrode conductors. The NEC specifies the requirements for grounding electrode systems, including the types of electrodes that are permitted, the minimum size of grounding electrode conductors, and the methods for connecting the electrodes together. It is important to follow these requirements to ensure that the grounding electrode system is effective in providing a low impedance path to earth. In addition to providing a low impedance path for fault current, grounding also helps to reduce electrical noise and interference. Electrical noise can cause problems with sensitive electronic equipment such as computers and communication systems. Grounding helps to minimize electrical noise by providing a path for unwanted currents to flow to earth, rather than interfering with the operation of the equipment. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of an electrical system together to create an electrically conductive path. This helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electrical shock. Bonding is typically accomplished by connecting metal conduit, enclosures, and equipment together with bonding jumpers or bonding conductors. The NEC specifies the requirements for bonding, including the types of bonding conductors that are permitted, the minimum size of bonding conductors, and the methods for connecting the conductors together. Regular inspections and testing of the grounding system are essential to ensure its continued effectiveness. Grounding systems can degrade over time due to corrosion, damage, or loose connections. Regular inspections can help to identify potential problems before they become serious hazards. Testing the ground resistance can help to verify that the grounding system is providing a lower impedance path to earth. If the ground resistance is too high, it may be necessary to install additional ground rods or make other improvements to the grounding system. When working on electrical systems, it is important to follow safe work practices to prevent electrical shock. Always energize circuits before working on them, and use appropriate personal protective equipment, such as rubber gloves and safety glasses. If you are not qualified to work on electrical systems, hire a licensed electrician to perform the work. Only qualified individuals should work on electrical systems. Improperly installed or maintained electrical systems can be dangerous and can pose a serious risk of electrical shock. Hire a licensed electrician to perform any electrical work that you are not qualified to do. By following these guidelines, you can ensure that your electrical system is properly grounded and bonded, reducing the risk of electrical shock and equipment damage. Remember, electrical safety is everyone's responsibility. If you have any questions or concerns about electrical safety, consult with a qualified electrician or electrical engineer. Additional points to consider when grounding parking lot lights include the type of soil in the area. Soil resistivity can affect the effectiveness of a ground rod. High soil resistivity requires longer or multiple ground rods. Check local codes. Some municipalities have more restrictive codes regarding grounding. Follow manufacturer instructions for any specialized grounding or bonding procedures. Document all grounding and bonding work performed, including the location of ground rods, the size and type of grounding conductors, and the results of any ground resistance testing. The purpose of all of this is to ensure the safety and effectiveness of the lighting system and its grounding components.